In this section, we will discuss the Hall effect, which is used to measure the carrier concentration and mobility of electronic materials. The Hall effect is based on the Lorentz force, which you'll recall from physics is the force that a moving charge experiences when it's in a magnetic field. Our positive charge here, pictured in blue, is moving to the right with velocity v. Because it is moving in a magnetic field B, here depicted as coming out of the board, it experiences a Lorentz force. To find the force on our particle with positive charge plus q, we use the Lorentz force law, force equals qv cross b. To find the cross product, we use the right-hand rule, with v pointing to the right and b coming out of the page, the force is then down. We get the same downward force for a negatively charged electron moving this time to the left because our Lorentz force law uses q times v in the cross product. Now imagine we have a sample material, shown by this rectangle, placed in a magnetic field coming out of the board, and that the sample contains mobile electrons. Now suppose we put electrodes on the left and right side, hook them up to a battery that runs a current from one side to the other. Suppose that this current is carried by negatively charged electrons that move to the left with average drift velocity Vd. Because these electrons are moving to the left with velocity Vd in a magnetic field coming out of the board with strength B, they will feel a downward force given by EVB from the Lorentz equation. With all the electrons in the sample moving downward, they will build up on the bottom side of the sample and deplete the top side, producing a net positive charge on the top and a net negative buildup of charge on the bottom that one could detect by means of a voltmeter connected from the bottom to the top of the sample. This voltage is known as the Hall voltage, V sub h, and is described by an electric field moving from top to bottom, which is perpendicular to the current moving from left to right. The negatively charged electrons experiencing the electric field from the Hall voltage are repelled from the bottom and attracted to the top. This imposes an additional upward force on our electrons given by the charge of the electron times the Hall electric field. Under steady-state conditions, this upward Hall force will exactly cancel the downward Lorentz force, preventing any further buildup of charges and giving us a constant Hall voltage. Thus, in our steady-state equilibrium, we can equate our Hall force with our Lorentz force, where our Hall force can be measured by our Hall voltage, and our Lorentz force is essentially a measurement of our drift velocity. The Hall coefficient, also described as a Hall resistance, is the ratio of the Hall electric field that's perpendicular to the applied current. Now, from the last slide, we know that the Hall force is equal to the Lorentz force, and so we have our Hall resistance is the drift velocity times the magnetic field, and we have that minus sign hiding in there, over the electric field. And then for the current, we'll use from before NE drift velocity. Then we see that the magnetic field cancels, the drift velocity cancel, and we end up with the Hall coefficient is simply negative 1 over E times the density of charge carriers. Thus, we have an easy way to measure N, the charge carrier concentration, or density of charge carriers. Now recall from sigma equals NE mu, combining resistivity measurements, which give us the electrical conductivity, with Hall measurements, which give us the charge carrier concentration, we also have a measurement of the mobility, which we also call the Hall mobility when we measure it this way. The Hall coefficient of select elemental metals is shown in this table, where the measured values gives us carrier concentrations which are typical of the values we'd expect from the density of atoms. And now we have Hall mobilities measured that we can use to understand electrical transport in these metals. The experimental Hall effect for most of these metals is negative, indicating the negative charge of the electron, although we will see there are cases where the charge carriers has an effective charge that's positive, and we will call these holes.